This is the continuation video in the playlist of geometrical isomerism. In this, we are going to discuss geometrical isomerism in a cumulene. Before going to geometrical isomerism directly, first let us understand what is the exact meaning of cumulene. What is the simplest example of a cumulene? Its orbital structure, orientation of pi bonds, orientation of sigma bonds. If you know all these details, then you can understand what kind of cumulenes exhibit geometrical isomerism and what type of cumulenes do not exhibit a geometrical isomerism. The compounds which are having two or more consecutive double bonds. If the given compound contains two or more consecutive double bonds, then it is said to be cumulene. And the simplest example of a cumulene is alene. Simplest member means that should have minimum number of carbon atoms. Minimum number of carbon atoms means that should have at least two double bonds. In order to have two double bonds, there must be three carbon atoms. As a result, the molecular formula of the compound becomes C3H4 and its degree of unsaturation is 2. So, the molecular formula of alene is C3H4. So, alene is the simplest member of cumulene and its molecular formula is C3H4, double bond equivalence is 2. And its IUPAC name is propadiene. If you see the formation of propadiene, if you see the formation of alene, then it will be easy to understand what type of cumulenes exhibit geometrical isomerism, what type of cumulenes do not exhibit geometrical isomerism. Instead of giving the condition, I just wanted to explain everything in detail. So this is the structure of alene. This is a two-dimensional structure. This is the first carbon, second carbon, third carbon, whatever. So these are the terminal carbons and this is the middle carbon. If you see the three-dimensional structure, the correct structure, the real structure, here one terminal carbon and another terminal carbon, orientation, hydrogens orientation, if you see here, this terminal carbon hydrogens are lying on plane of the paper, but hydrogens of another terminal carbon, they are not in the same plane. One is above the plane, one is above the plane, another one is below the plane. First, we need to understand the exact reason for this. Then you can understand whether the given alene or alene derivative cumulene shows geometrical isomerism or not. To understand this, why the structure is like this, why 3D structure is like this, why these hydrogens are not in the same plane. For that, first we need to take a formation of alene, that is with the help of hybridization. So here, this is same, that is alene, and if you see, this carbon is sp2 hybridized, this is also sp2 hybridized, this is sp hybridized. The first excited state of carbon, so here there are totally 4 unpaired electrons, and these are the 3 carbons of alene, and terminal carbon undergoes sp2 hybridization, middle carbon is sp hybridized, another terminal carbon is also sp2 hybridized. For the sake of convenience, here I am taking the unhybrid orbital is py, hybrid orbitals are px and pz. Px and pz. With this you will understand the orientation of pi bond between first and second carbon, second and third carbon. And here the middle carbon, let me take this is py, this is pz, and of course px orbital is going into hybridization. But here I am taking pz orbital, another terminal carbon pz orbital. You will also understand why it is pz orbital. Why not py orbital? You will understand. So obviously this will be px and py orbitals. Now if you carefully observe, this terminal carbon has totally 3 hybrid orbitals, and these 3 hybrid orbitals will form sigma bonds, and these are the 3 sigma bonds. These are the 3 sigma bonds. If you carefully observe, this terminal carbon has utilized px and pz orbitals. Therefore, here the sigma bonds are in xz plane. This terminal carbon, one terminal carbon which is using px and pz orbitals for hybridization, the sigma bonds will be in a xz plane. Another terminal carbon, if you see px and py orbitals, therefore these sigma bonds, that is 3 sigma bonds of another terminal carbon, they are in xy plane. So obviously one terminal carbon sigma bonds are in xz plane, another terminal carbon sigma bonds are in xy plane. So it means they are perpendicular to each other. And similarly, here the py orbital of this terminal carbon, py orbital of middle carbon, they undergo sidewise overlapping. You can see this orbital picture. This is py orbital. This is py orbital. These are the py orbitals of one terminal carbon and middle carbon. This is internuclear axis. X-axis is internuclear axis. And obviously these orbitals undergo sidewise overlapping. Above and below internuclear axis, there is a pi electron density along y-axis. So here this is py orbitals sidewise overlapping. And here another overlapping, sidewise overlapping, if you see pz orbital of middle carbon and pz orbital of another terminal carbon, they also undergo sidewise overlapping. You can see this is pz orbital. If you see the middle carbon, it is using py and pz orbitals to form pi bonds. This is pz orbital, this is pz orbital, and these are undergoing sidewise overlapping. As a result, there is a pi bond that is along z-axis. Here, this is py overlapping, this is pz overlapping. Due to that particular reason, you can see, so this is the pi bond between one terminal carbon and middle carbon. This is the pi bond between middle carbon and another terminal carbon. The 2 pi bonds are perpendicular. You can see one pi bond is like this, another pi bond is like this. Sigma bonds are perpendicular. Sigma bonds are not in the same plane. Pi bonds are also perpendicular. So this is about a formation of allene, formation of C3H4. Now you can see the pi bonds here. This is pi bond, this is a pi bond. Of course, this is internuclear axis. Here already I mentioned, here the sigma bonds are in xz plane. Here the sigma bonds are in xz plane. Here the sigma bonds are in xy plane. Here this pi bond that is due to py orbitals. Here this is due to pz orbitals. Therefore, the real structure of allene, if you see, so here this pi bond and this pi bond are perpendicular. If one pi bond is like this, another pi bond will be like this, and they are perpendicular. And even if you see these 2 sigma bonds, of course here there is one more sigma bond. You can see these 2 sigma bonds and these 2 sigma bonds are perpendicular, because here these are in xz plane, but here these are in xy plane. So this is the reason why the 2 pi bonds are perpendicular. You can see here at this carbon, if these are lying in the plane of the paper, this is above the plane and this is below the plane. This is nearer to the observer, this is away from the observer. So very clear, here the groups and here the groups are not in the same plane. You can see here the pi bond here and the pi bond here are perpendicular. Distance between these two and between these two absolutely same. So this is about allene formation. What is cumulene? What is allene? Allene formation. The sigma bonds of terminal carbons, the pi bonds, the 2 pi bonds, how they are oriented, clearly we discussed. Before going to the conclusion, let us take a cumulene with the odd number of double bonds. Let me take here totally 3 double bonds I am taking. For that I need to take 4 carbon atoms. Of course, these are the first excited state configurations of 4 carbon atoms of the given molecule. This is again sp2 hybridized. This is also sp2 hybridized. I am taking here, this is sp2 hybridized. For the sake of convenience, again I am taking, this is py orbital. Py orbital is not involving in the hybridization. This is one carbon. Here this is sp hybridized. So here this is unhybrid orbital, py orbital, pz orbital. Again this is also sp hybridized, unhybrid orbital, py orbital and pz orbital. But this is again terminal carbon. Its hybridization is sp2. Here py is unhybrid. Now here we have to take again py is unhybrid. Now what will happen here, these orbitals will form sigma bonds. It's very clear. This is px and pz, px and pz. So these sigma bonds are in a xz plane. These sigma bonds are also in xz plane. So okay, first let us see the sidewise overlapping of orbitals. So py orbital of this will undergo sidewise overlapping. So here py orbital and py orbital sidewise overlapping, that is along y-axis. So here pz orbital and pz orbital here sidewise overlapping. Py orbital and py orbital again sidewise overlapping. Just pause the video and understand it properly. So this is py and py. So obviously py is involved here. One more orbital is pz. Here it is obviously pz. This is also using pz orbital. And another unhybrid orbital is py. This py and this py will undergo sidewise overlapping. So what I am trying to convey here is this pi bond is py py, this pi bond is pz pz, this pi bond is py py. Ultimately this pi bond and this pi bond are in the same plane. You can see. So here for the sake of convenience I am writing, this is py orbital, pz orbital, this is pz orbital, this is py, this is py. You can see these sigma bonds and these sigma bonds are in the same plane, and here this pi bond and immediate pi bond are perpendicular, this pi bond and next pi bond are perpendicular. Ultimately this pi bond, this one and this one are in the same plane. These hydrogens are also in the same plane. Understand it properly. So here these two are perpendicular, these two are perpendicular. Ultimately what I am trying to clearly here I mentioned, here the sigma bonds in xz plane, here the sigma bonds in xz plane. So here this is py py, this is py py, and here this is pz pz. Ultimately in case of cumelenes with the odd number of double bonds, this is the real structure. You can see these atoms are in the same plane. Distance between these two groups and distance between these two groups is definitely not same. If I say this is the distance L1 and this is the distance L2, undoubtedly this distance is more. In the previous case they were perpendicular. You can see this is above the plane and this is below the plane. Distance is the same, but in the present case they are in the same plane. You can see they are in the same plane. So here distance between these two atoms and distance between these two atoms, definitely those distances are not same. And here the structure balanced model, if you see, this pi bond and this pi bond are in the same plane, and here the distance and here the distances are definitely not same. And this is about cumulene with the odd number of double bonds, cumulene with the even number of double bonds. Finally, if you see the conclusion, Cumelenes with even number of double bonds do not show geometrical isomerism. Cumulene with even number of double bonds, you can see once again the same picture I am using. Geometrical isomerism is not possible because the distances are same. These groups and these groups are not in the same plane. So obviously the distances are same. Therefore, cumulines with even number of double bonds, whatever it may be the groups attached to the terminal carbons, those double bonds are not geometrical centers. But cumulines with odd number of double bonds, they show geometrical isomerism if terminal carbons have AB type of structure, AD type of structure, or ABDE type of structure. That means the terminal carbon should be attached to two different groups. Normal alkene case, 100% the normal alkene case. So when you are dealing with the cumulines, in order to check geometrical isomerism possibility, two important points you have to consider. The first one, it has to have odd number of double bonds, and also the groups attached to the terminal carbon must be different. So the two terminal carbons may have either AB type of structure, ABAD type of structure, or ABDE type of structure. In these two cases, we use cis-trans nomenclature, and here we use EZ nomenclature. So if you take allene with the odd number of double bonds, just now we discussed, these groups and these groups are in the same plane. In that situation, you can say here the distance is less, here the distance is more, but here the groups attached to the terminal carbon must be different. Here you see A and B, here also you have A and B. So in that situation, geometrical isomerism is definitely possible. So let me take one example here. So this is a C double bond C double bond C double bond C, cumulene with odd number of double bonds. These sigma bonds and these sigma bonds are in the same plane. Here I am taking CH3, here I am taking OCH3, here it is hydrogen, and here it is chlorine. So cumulene with the odd number of double bonds, these bonds are in the same plane. Already clearly I explained. CH3, OCH3 different groups, hydrogen and chlorine different groups. So no common groups at the terminal carbons. We have to use EZ nomenclature. In case of EZ nomenclature, you have to use CIP rules. First priority, second priority, first priority and second priority. So here high priority groups are same side, therefore it is said to possess Z configuration. For example, if you have cumulene with even number of double bonds, in that situation, just now I discussed 1, 2, 3, 4 even number of double bonds. In that case, the two sigma bonds here, for example, I am taking CH3 and hydrogen, but these are not in the same plane. The sigma bonds of one terminal carbon, sigma bonds of another terminal carbon are not in the same plane. But in the exam, they will not mention like this. But you need to understand here the distance between CH3 hydrogen, CH3 is the same. Even if you interchange the position of this hydrogen and methyl, they are not geometrical isomers. They are not geometrical isomers because here the distance and here the distance is the same. So this is about geometrical isomerism in cumulines.